In 1993, Ford put a 32-valve, dual overhead cam, all-aluminum V8 into a Lincoln. Not a Ferrari, not a Porsche, a Lincoln. The engine block was cast in Italy by the same company that made blocks for Formula One teams, and Ford used it to move a 2-ton luxury coupe to the country club. That's either the most ambitious engine program in American automotive history or the most expensive way to confuse your customer base. Probably both. So here's where this story starts. In the mid-1980s, Ford had a problem. Actually, Ford had several problems, but the one that matters here is that their V8 engines were old. Not just could use a refresh old. We're talking designs from the early 1960s. The Windsor small block, the 385 series big block, these things had been around longer than most of the engineers working on them. They were pushrod engines, 2 valves per cylinder, cast iron, everything. And while they'd served Ford well for decades, the world was changing around them. Japanese and European automakers were building overhead cam engines with 4 valves per cylinder, revving higher, breathing better, and making more power from less displacement. BMW had their inline 6s. Toyota had the legendary 1UZ V8 in the Lexus LS400. Honda was doing things with VTEC that made American engineers quietly nervous. Ford's V8s were reliable and cheap to build, but they were falling behind on power density, emissions compliance, and fuel efficiency. The gap was widening every year. Enter Donald Peterson, Ford's chief executive officer. Peterson had already shaken up Ford's design philosophy, pushing the company away from boxy styling toward the sleek, aerodynamic look that produced the Taurus. Now he wanted the same revolution under the hood. He tapped a senior engineer named Jim Clarke and gave him a straightforward but massive assignment. Build a new V8 from scratch. Make it better than everything Ford had ever done. Make it better than what the imports were doing. And make it work across the entire product line, from luxury sedans to pickup trucks. Clarke and his team didn't just sketch something on a napkin and call it a day. They conducted an exhaustive study of engine designs from every major manufacturer on the planet. They looked at what BMW was doing with overhead cams. They studied Toyota's casting techniques. They analyzed the way European manufacturers were achieving power density without sacrificing smoothness. The goal wasn't to copy anyone, it was to leapfrog everyone. What they came up with was the modular engine family, and right away, the name caused confusion. Modular didn't mean the parts were interchangeable between different versions. It referred to the manufacturing process. Ford designed a flexible tooling system that could produce different engine configurations, from single overhead cam 2-valve versions to dual overhead cam 4-valve versions, all in the same factory with minimal changeover time. This was a big deal for production efficiency. It was not, however, a big deal for the guy in his garage trying to swap parts between a Lincoln and a Mustang. Those parts didn't swap. The name was misleading from day one. Ford committed $4 billion to the program. In 1980s money, they retooled their old tractor plant in Romeo, Michigan, specifically to build these engines. $4 billion. For context, that's roughly $9.5 billion in today's dollars. For an engine program, that is not a company hedging its bets. That's a company burning the boats on the beach. The first modular engine appeared in the 1991 Lincoln Town Car. It was a 4.6-liter single overhead cam 2-valve V8, making 190 horsepower, respectable for a luxury barge. Nothing to write home about for performance enthusiasts, but it was just the opening act. Behind the scenes, Ford was working on something far more ambitious, a version of the 4.6 with dual overhead cams, 4 valves per cylinder, and an all-aluminum construction, 32 valves total, 4 camshafts, in an American V8. In the early 90s, this was not normal. American V8s were supposed to be big, heavy, iron block pushrod engines that made torque down low and called it a day. What Ford was building looked more like something out of a European exotic car catalog. And here's where the Italian connection comes in. Ford needed an aluminum block for this engine, but casting aluminum V8 blocks was still something of a dark art for most American manufacturers at the time. So Ford went to Teksid, a company based in Italy owned by Fiat. Teksid had been casting engine blocks since the late 1970s. They supplied blocks for Ferrari. They supplied blocks for other Formula One constructors. Their aluminum casting process was, at the time, among the best in the world. The Teksid block was a 6-bolt main-bearing cap design cast in SAE 319 modified alloy aluminum, then heat-treated and aged to achieve the desired characteristics. It weighed about 85 pounds. Bare, just the block. The iron blocks Ford was using for the 2-valve version weighed significantly more. But the real story wasn't the weight savings, it was the strength. That Teksid casting was absurdly strong for a production aluminum block. Aftermarket tuners would later discover that a properly prepared Teksid block could handle 1,200 horsepower. Some pushed them past 1,500. A few lunatics got north of 2,000. From a Lincoln engine, cast in Italy, for a car that came with a leather bench seat and a cassette player. The engine debuted in the 1993 Lincoln Mark VIII. 280 horsepower, 285 pound-feet of torque. For 1993 in a luxury coupe, those were strong numbers. The Mark VIII was a genuinely interesting car. It sat on its own platform designated FN10, despite starting development on the same bones as the Thunderbird and Cougar. It used an air suspension system. It weighed 30 pounds less than the car it replaced, despite being 4 inches longer and almost 4 inches wider. The all-aluminum engine and composite hood materials made up for the additional size, but the Mark VIII was a Lincoln. It was quiet. It was comfortable. It went to valet parking and golf courses. Nobody was racing them. The engine was dramatically overqualified for the job it was doing. It was like hiring an Olympic sprinter to deliver your mail. Meanwhile, across the Ford campus, something was brewing. In 1991, Ford had formed the Special Vehicle Team, SVT. This was the successor to the old Special Vehicle Operations Division that had produced the SVO Mustang in the mid-'80s. The mission was simple on paper, but difficult in practice. Build limited production, high-performance versions of existing Ford vehicles. Make them fast, make them handle, make them special, and don't lose money doing it. The man who would define SVT was John Coletti. A 30-year Ford veteran, Coletti was an engineer with the personality of a football coach and the conviction of a true believer. He's the guy who saved the Mustang from becoming a front-wheel drive Mazda platform. Yes, that almost happened. In the early 90s, Ford was seriously considering replacing the rear-wheel drive Mustang with a front-wheel drive car developed with Mazda. The public outcry was significant, but it was Coletti who led the internal opposition. He later said he would rather have seen the Mustang name die than put it on the probe. That's the kind of person he was. Coletti ran SVT with a 38-person team, tiny by automotive standards. But they were insulated from the bureaucracy that slowed down most of Ford's operations. Have fun was literally in the job description. The first SVT products debuted at the 1992 Chicago Auto Show, the SVT Mustang Cobra and the SVTF 150 Lightning. The Cobra was the one that got enthusiasts talking. Now, the 1993 Cobra was not the engine story we're here for. That car used a modified version of the old 5.0 pushrod V8 with GT40 heads and intake work, making 235 horsepower. It was good. It was the last great pushrod Mustang. But SVT was already looking ahead. In 1996, everything changed. The Mustang GT switched from the beloved 5.0 pushrod V8 to the modular 4.6 single overhead cam 2-valve engine. Mustang fans were furious. The new engine made 215 horsepower. The old 5.0 made 215 horsepower. Same number. Less character, less aftermarket support, less soul, if you believe the forum posts. And there were many, many forum posts. But the SVT Cobra got something different, something special. It got the dual overhead cam 4-valve version of the 4.6. The same basic architecture as the Lincoln Mark VIII engine, but tuned and assembled by SVT for a very different purpose. And this is where the over-engineering label starts to really stick. Every single 4-valve Cobra engine was hand-built. 2 SVT technicians assembled each motor at Ford's Romeo, Michigan plant, by hand, in a factory that also mass-produced engines by the thousands. These 2 guys would take the Teksid aluminum block, the Italian one, the one that could handle 1,200 horsepower, and carefully assemble a naturally aspirated engine that made 305 horsepower. 305 horsepower from a hand-built all-aluminum 32-valve dual overhead cam Italian block V8. The Chevrolet Camaro and Pontiac Trans Am were making roughly the same power from a 5.7-liter pushrod V8 that cost a fraction as much to produce. The GMLT1 was basically a warmed-over version of the small-block Chevy that had been around since Eisenhower. It was simpler, it was cheaper, and it made the same numbers. So why did Ford go through all this trouble? Because the numbers didn't tell the whole story. The Cobra engine revved. It had a character that the GM pushrod engines simply didn't possess. The wide DOHC heads dominated the engine bay, looking like nothing else in the American muscle car world. It sounded different. It pulled different. It felt exotic in a way that a Mustang had never felt before. Some enthusiasts hated the loss of the 5.0. Others recognized that Ford was building something genuinely forward-thinking. The engine also had a variable runner length intake manifold with intake manifold runner controls. Depending on the application, these were either vacuum-operated or electrically activated. Below a certain RPM threshold, the runners were long, optimizing low-end torque. Above that threshold, they shortened, allowing the engine to breathe better at high RPM. This was sophisticated stuff for a mid-90s American performance car. The split-port cylinder heads featured individual intake ports for each intake valve, 2 ports per cylinder, feeding the 4-valve combustion chambers. If you're enjoying this, hit subscribe. We cover engineering stories like this every week. All right, back to it. So how did this 32-valve masterpiece actually work compared to the competition? On paper, the 96 through 98 Cobra was competitive with the Camaro SS and Trans Am. 305 horsepower and 300 pound-feet of torque versus the GM cars, roughly 305 horsepower and 335 pound-feet from the 5.7-liter LS, one that replaced the LT1 in 98. But the Ford engine was doing this from 281 cubic inches. The GM engine displaced 346 cubic inches. The Ford was making almost the same power from nearly 20% less displacement. That's the trade-off of the DOHC design: more complexity, more parts, more cost, but also more efficiency per cubic inch and more potential for future development. Ford was playing the long game. The Camaro was playing the right-now game. The engine earned a spot on Ward's 10 Best Engines list for 1996 and 1997. That validation mattered. It told the industry that Ford's approach, building a technologically sophisticated engine for a mass-market performance car, wasn't just engineering hubris. It was genuinely excellent. Then came 1999, and things went sideways. Ford gave the Cobra a significant update for the new Edge body style. The engine got revised cylinder heads with tumble-style intake ports, where one port now fed both intake valves instead of having individual ports for each. New camshaft profiles. A fixed runner-length intake manifold replacing the variable system. On paper, these changes should have produced 320 horsepower and 317 pound-feet of torque, 15 more horses than the previous year. Progress. There was one problem. The engines weren't actually making 320 horsepower. Word started spreading through the enthusiast community almost immediately after the cars hit dealerships. Owners were reporting that their 99 Cobras felt slower than the 98 models they'd replaced. Some took their cars to dynamometer shops. The results were not good. Cars that should have been putting down somewhere around 270 horsepower at the rear wheels were showing numbers as low as 240. Some owners calculated that their engines were producing closer to 285 horsepower at the crank. That's 35 horsepower less than advertised. In the spring of '99, a cover story for Car and Driver put the Cobra head-to-head against the Camaro SS and Trans Am in a convertible shootout. The Cobra hit 60 miles per hour in 6 seconds flat. Both GM cars did it in 5.3. The magazine's executive editor grew suspicious. The more he drove the Cobra, the slower it seemed. By July '99, the story had blown up. Ford couldn't deny it anymore. They launched an investigation and found 3 separate problems. The cast aluminum intake manifold had manufacturing defects that were restricting airflow, costing 5 to 7 horsepower. A compression issue was robbing another horse. And the exhaust mufflers were being crushed during installation to clear the independent rear suspension, creating excessive back pressure and choking out another 7 horsepower. Add it all up, and the engine was roughly 15 horsepower short of its rating. Some individual examples were worse. On August 6, 1999, Ford announced they were canceling the 2000 model year Cobra entirely. Gone. No 2000 Cobra. They recalled all 5,399 Cobras that had been sold or were sitting on dealer lots. The fix involved 4 things. New intake manifolds. Some early replacements were extrude-honed and marked with a blue dot. Later units were cast from acid-dipped cores and marked with a green dot. New mufflers that weren't crushed. A recalibration of the engine control computer, and a new belt tensioner for good measure. Ford took the hit. They ate the cost. And they killed an entire model year rather than risk shipping another batch of underperforming engines. Say what you want about the screw-up, but canceling a model year because the car wasn't fast enough is a power move. Most manufacturers would have quietly updated the parts and hoped nobody noticed. Ford pulled the plug. Coletti and SVT refused to release a product they weren't proud of. When the 2002 Cobra also didn't meet their standards during development, they canceled that model year too. 2 gaps in production because the car wasn't good enough. That's either admirable or insane. Maybe both. Now let's talk about what this engine really was under the skin. The 4.6-liter displacement came from a bore of 3.55 inches and a stroke of 3.54 inches, nearly square. This is significant because a square bore-to-stroke ratio favors high RPM breathing and smooth operation. Exactly what you want from a high-revving multi-valve engine. The compression ratio on the naturally aspirated Cobra versions ran around 9.85 to 1. The cylinder heads were the star of the show. Each head carried 2 overhead camshafts, one for intake, one for exhaust, actuating 4 valves per cylinder through low-friction, direct-acting bucket tappets. No rocker arms, no push rods. The cam sat directly over the valves and pushed them open through inverted bucket-style followers. This reduced valve train mass and friction, allowing higher RPM operation with less risk of valve float. The early heads, used from 93 through 98, were the split-port or B-head design. Each intake valve got its own individual port in the head. This gave excellent port velocity at lower RPM and strong mid-range torque characteristics. The trade-off was that the ports were somewhat restrictive at very high RPM. The The 99 and later tumble port or C-head design merged the two intake ports into one larger port that fed both intake valves simultaneously. This improved high RPM airflow at the cost of some low-end response. The tumble effect, where the incoming air charge rotated within the combustion chamber, improved fuel-air mixing and combustion efficiency. The ignition system was coil-on-plug. Each cylinder had its own individual ignition coil sitting directly on top of the spark plug. No distributor, no plug wires. This was cutting edge for the mid-90s and provided more precise ignition timing and higher available voltage at the plug gap. Fuel delivery was sequential multi-port injection controlled by Ford's EEC 5-engine management computer. Each injector fired once per engine cycle, timed to each cylinder's intake stroke. The throttle body was mechanical on early versions, transitioning to electronic throttle control on later applications. The bottom end was built to take abuse, even though it didn't need to in stock form. The Cobra versions used a forged steel crankshaft with 8 flywheel bolts, heavier duty than the Lincoln's cast iron crank with 6 bolts. The connecting rods were powder metal forgings, strong enough for the stock 300 horsepower application with plenty of margin. The Teksid block's 6-bolt main caps kept everything clamped down tight. All of this engineering, the aluminum block cast in Italy, the 32-valve heads, the coil-on-plug ignition, the variable intake manifold, the hand assembly, it produced 305 horsepower in a naturally aspirated application. A contemporary Honda S2000 made 240 from 2.0 liters with similar technology. Per liter, the Honda was more efficient. But per dollar and per unit of displacement, the Ford was competitive with anything in the world that wasn't wearing a European badge and a 6-figure price tag. The consequences of Ford's DOHC gamble rippled outward in ways nobody fully anticipated. The most dramatic example came from Sweden, of all places. In the early 90s, a 22-year-old named Christian von Koenigsegg founded a company with no automotive manufacturing experience and an audacious goal: build the world's greatest sports car. When he needed an engine, he turned to the Ford Modular 4.6 DOHC. He and his small team took the architecture, enlarged it to 4.7 liters, added a supercharger, forged internals, dry sump lubrication, and pushed it to 655 horsepower. The result was the Koenigsegg CC8S, which debuted in 2002 and won the Guinness World Record for the most powerful production car engine. 6 examples were built. The follow-up CCR doubled down with twin superchargers, producing 806 horsepower from the same basic Ford architecture. In 2005, it set the world record for fastest production car at 241 miles per hour at the Nardo test track in Italy, a world speed record, set by a car powered by an engine that shared its fundamental design with a Lincoln luxury coupe. Koenigsegg eventually moved on to their own bespoke engine designs, but the Ford modular architecture provided the foundation that launched one of the most prestigious hypercar brands on the planet. Jeremy Clarkson named the CC8S his favorite supercar of 2004. It beat Ferraris and Lamborghinis and Paganis. Powered by a Ford. The DOHC 4.6 also found its way into the Panos Roadster and Esperante, the MG X-Power SV, and various race applications. The engine's combination of compact dimensions, aluminum construction, and enormous headroom for forced induction made it attractive to small-volume manufacturers who needed a powerful, reliable V8 without the budget to design their own. Back at Ford, the DOHC program reached its apex with the 2003 and 2004 SVT Cobra, internally codenamed Terminator. Coletti named it himself. His reasoning was straightforward. GM had just canceled the Camaro and Firebird for 2003. The pony car war appeared to be over. and Coletti wanted to build the car that would have terminated the competition had they stuck around. The Terminator took the 4.6 DOHC and bolted on an Eaton M112 Roots-type supercharger, pushing 8 pounds of boost through a water-to-air intercooler. To handle the additional stress, SVT switched from the aluminum Teksid block to a cast-iron block with 4-bolt main bearing caps. Stronger internals went in, including forged Zollner pistons and Manley H-beam connecting rods. The compression ratio dropped to 8.5:1 to accommodate the boost. A Tremec T56 6-speed manual transmission replaced the previous 5-speed. The result was 390 horsepower and 390 pound-feet of torque, officially. In reality, the Terminator was underrated. Owners routinely dynoed their cars at 380 horsepower at the rear wheels. Working backward through drivetrain losses, the engines were actually making somewhere around 420 to 430 at the crank. Ford underrated it by about 40 horsepower. After the '99 debacle, where they'd overstated the power, they went the other direction. They sandbagged it. Nobody complained. The Terminator could run the quarter mile in the low 13-second range on stock tires with a stock tune. With a simple pulley swap to increase supercharger boost and a tune, mid-11-second passes were common. The car had so much latent potential that the aftermarket exploded around it. And that iron block, the one Coletti chose because aluminum blocks kept failing during development testing, it could handle well over 1,000 horsepower at the rear wheels with proper supporting modifications. The DOHC 4.6 was discontinued along with the rest of the modular engine family when the 5.0 Coyote arrived for the 2011 model year. But the Coyote was a direct evolutionary descendant of the modular program. It used the same bore spacing, the same bell housing bolt pattern. It was built on the same production tooling. The $4 billion investment that started in 1987 was still paying dividends more than 2 decades later. The Teksid aluminum blocks have become collector items. Tuners hoard them. A good used one in the right condition can command several $100s, which might not sound like much until you realize these are bare engine blocks from $99 Lincoln Mark VIIIs that nobody wanted when they were new. The irony of the Ford 4.6 DOHC is that it was simultaneously too much and not enough. Too much engineering for the applications Ford initially chose, an Italian cast aluminum block capable of 1,200 horsepower being used to make 280 in a Lincoln. Hand-built engines for a Mustang that cost under $30,000. A 32-valve architecture competing against pushrod 5/8s that made the same power for half the manufacturing complexity. But also not enough. Not enough power to consistently beat the cheaper, simpler GM alternatives on the street. Not enough displacement to deliver the low-end torque that American V8 buyers expected. Not enough aftermarket support in the early years, when 5.0 guys could build a 300-horsepower engine from junkyard parts, and the modular guys needed specialized tools and expensive components. Ford built the future before the market was ready for it. They spent $4 billion to create an engine family that would dominate for 20-plus years. But the first decade was an uphill battle against customers who just wanted a bigger pushrod motor. The DOHC 4.6 was proof that being right and being popular aren't always the same thing. Today, the Coyote V8 that descended from this program makes 480-plus naturally aspirated horsepower and revs to 7,500 RPM. It's one of the most celebrated engines in the modern automotive world. Nobody calls it over-engineered. They call it one of the best V8s ever made. But it only exists because Ford had the conviction and the budget, and maybe a touch of insanity, to build a Formula One supplier aluminum block 32-valve DOHC V8 for a Lincoln in 1993. That's the legacy. Ford didn't just build an engine, they built the template for the next 3 decades of American V8 performance. They just had to survive a horsepower scandal, 2 canceled model years, billions in development costs, and an entire generation of Mustang owners who missed the 5.0 to get there. And there you have it. The Ford 4.6 DOHC, an Italian-cast, hand-built, 32-valve answer to a question that most of America hadn't even asked yet. If you've owned one of these, worked on one, or just appreciated what Ford was trying to do before the rest of the industry caught up, let me know in the comments. And if you made it this far, subscribe. We do this every week.